Uh, Good afternoon, all. Uh, in today's lecture, we'll be discussing Newton-Raphson methods and secant method and their geometric interpretation. So, let us start. Good afternoon, all. My name is Nitin Tomar, and in today's session, we are going to discuss some further topics in our journey of numerical analysis. So, today we start with the secant method. So we start with the algorithm. So we start with the algorithm of the secant method. Let us present the algorithm of the secant method. So what are the hypotheses? Given any initial values, x naught and x. One such that f of x naught is not equal to f of x1, f is the function whose roots need to be calculated over an interval. So the algorithm is step 1. For n equal to 1, 2, up to so on and so forth, we give the iterative sequence formula. The iterative sequence for secant method is given by this. Xn plus 1 is actually f of xn times xn minus 1 minus f of xn minus 1 xn, then f of xn minus f of xn minus 1. This expression can also be written as xn plus 1 equal to xn minus f of xn minus xn minus 1 upon f of xn minus f of xn minus 1. So these two are the same equation. Now step 2. Yes, so this is the formula for the secant method. Now, why do we use secant method? Okay, so see, okay, I should write it like this. The aim of the secant method. Okay. The secant method is a root finding algorithm and why is it called a secant method? Because it uses a succession of roots of secant lines To better approximate the root of function f, the root of function f, okay, so geometrically what is happening, see, so for example you have this x-axis and y-axis, and let's say this is your curve. Now for example, the first two approximation you took here, x naught and let's say x1, okay, so this is this point, and x naught is this point, yeah, so this is my x naught and this is the point f of x naught, yeah, this is my f of x. Now what you do, you join these 2 points, okay, maybe I should for the clear better understanding, okay, just a minute, huh? Yeah, that's fine. So now you join these 2 points. Yes. So the point, so this is called the secant line, and you join these 2 points. The point at which this intersects x-axis is your second iteration. And this is called x2. See, x2 is this equation of line, and this is precisely the blue line. Then so here you'll have this. Yes. Now join x1 and x2 again. So the point at which this intersects, again same logic, and you keep on doing this. So in this way we will get our next iterations, and this is precisely the algorithm. So maybe we can derive the method. So why, from where does this equation comes? So let's see the derivation. Starting with initial values x0 and x1. So what we did, so what we saw in the geometric picture, we'll just do it here mathematically. We construct a line through the points x0 comma f of x0 and x1 comma f of x1 as discussed above. In the picture, and what will be the equation of line? So you have to have a line through the points x0 comma f of x0 and x1 comma f of x1. So the equation of this line is y equal to f of x1 minus f of x0, x1 minus x0 times x minus x1 plus f of x1, right? This is the line that passes through x0 comma f of x0. Yes. So this is the line. Now once we have this, the root of this linear equation, that is x such that y equal to 0 is given by, you just solve y equal to 0. So what we have done, we have just put y equal to 0 here, and the same thing yeah. So if we solve this, what does it imply? It implies x is x1 minus f of x1, x1 minus x0 times f of x1 minus f of x0, right? See, because what we did, we first joined this line passing through x0 and x1, and the next iteration is this, the root of this equation. Okay, let's say this is, yeah. So precisely what we have explained in the geometric picture, we are doing that. So we then use this new value of x as x2 and repeat the process using x1 and x2 instead of x0 and x1. And we continue this process continue this process such that such that given a real number alpha, so you fix a real, so such that okay, I'll write it this way, such that sufficiently high level of sufficiently high level of precision is obtained. And what do we mean by that? A sufficiently small, a sufficiently small difference between the nth iteration and the n minus 1th iteration. So if you keep on doing this, you will get x2. You just look at this. So our x2 was this. Now, how will you obtain x3? It will be same as the previous iteration, just the points being yeah, point being changed accordingly. And you keep on doing this, and you will get the formula. By induction, you will get the formula. So this is by induction. Yeah. So this is the precise required formula. Now let us discuss the convergence. Let us discuss the convergence. So I will not prove the order of convergence. Just I will just say a few things about it. First, the I the iterants the sequence of xn obtained in the secant method converge to a root of f if the initial values x0 and x1 are close enough to the root. Moreover, The order of the convergence, we know what do we mean by the order of convergence. We have discussed it in the previous session. The order of the convergence for this method is phi, which is the golden ratio, and it is equal to 1.618 something. So hence we say that the convergence is super linear but not quadratic. It is super linear but not quadratic. Okay. Now, as any other method, we'll see some drawbacks of the method. Drawbacks of the secant method. Number one, the drawback is if the initial values are not close enough to the. Okay, just a minute, my screen just froze. So, if the roots are not close enough, if the initial values are not close enough to the roots, then there is no guarantee that the secant method converges. The secant method converges. So yeah. So now let us see a few examples of this method being applied. Example: sin x plus x square minus 1 equal to 0. So we let the initial values to be x0 to be 0 and x1 to be 1. This is just for the sake of applying the method so that you know how to. It is a formula based method, so you have to put the values every time. Yeah. Then the iterations from the secant method are given by the following. So we'll compute one by one. I'll show one. Okay. So what is the formula of x2?
Hello, Anuj. Am I audible?
Yes,
Okay. So, do you have any doubt?
sir. Click on the Numerical session.
Yes.
मैंने स्पीड का भी देखा है नुकसान।
Oh, okay. Uh, okay, then I was teaching secant method. I will continue with that. Okay. Hmm.
So here is the formula for x2. So this will be, because x1 is 1, minus f of x1 will be sine 1, right? Yes. So it will be sine 1, and x1 minus x0 will be 1 upon f of x1, which is sine 1, minus x0, so 0 0, and this is minus minus plus 1. So you solve it, and you will get somewhere around 0.543044. Okay, so this is how, okay, so similarly your x3 will be x2 minus f of x2, x2 minus x1 upon f of x2 minus f of x1. And if you compute, you just plug in the values, so it will be 0.62663, and let's say x4, the formula for x4 will be x3 minus f of x3, x3 minus x2, f of x3 minus f of x2. So this value will be 0.637072. Okay, let fifth be the last iteration. x5 will be x4 minus f of x4, x4 minus x3 by f of x4 minus f of x3, 0.636732. Yeah, so you see the values are now, it seems to be converging to 0.63 something, right? In fact, in fact, the exact value of the root up to 6 significant digits is are approximately equal to, or let's say is 0.636733. You see, so the fifth iteration has only the gap of 0.00001, and we have already seen this in the bisection method. So, and we have seen that the order of the bisection method is linear, or at least it is not super linear. So the secant method converges faster than bisection method in this example. In this example. Okay, so as we have discussed, the convergence of A secant method is superlinear. So let us see the full statement theorem. Convergence of secant method.
Anuj, am I audible? Hello? Hello, Anuj, am I audible? So, do you know convergence of. You're outside?
नहीं सर वो हॉस्टल का थोड़ा वो वाईफाई से नहीं काम कर रहा
Okay. Okay, okay. So, do you know convergence of secant method? Do you know convergence? What do we mean by convergence?
जब किसी एक सर्टेन इंटरवल में आपको कोई वैल्यूज कन्वर्ट करते हो किसी इंटरवल में
Okay, then you listen carefully. Okay.
So if we start with the C2R function, R to R be a C2R function, which means twice continuously differentiable function. Be a C2R function. Maybe I should write it in the next line. Yeah, so it is a C2R function. And let R be a simple root. R be a simple root of the non-linear equation fx equal to 0, that is f prime r is not equal to 0. Then there is a delta greater than 0 such that for every x0 x1 in r minus delta and r plus delta, which means if you're close enough to the root, number one, such that number one, the secant method, the secant method iterative sequence xn is well defined. Secondly, the sequence xn belongs to the interval r minus delta, r plus delta. Third is xn converges to r, and we have that the order of convergence, which is what is the order of convergence? The order of convergence is xn plus 1 minus r mod upon xn minus r alpha as n goes to infinity. So this limit exists and it is alpha by alpha plus 1, where alpha is obviously, as discussed, is the golden ratio, where alpha is 1 plus root 5 by 2, approximately equals to 1.62. So up until now, at this point, what we have done, we have discussed an algorithm of a root finding method, which is called the secant methods. And how does it work? So you start with two initial values, you pass a line, you join these 2 points via the line, which is called the secant. Okay, and this line, the line, this line intersects x's at some point, and the point of intersection is your next iteration, say x2, and again you join x2 and x1. Again you join f of x2 and f of x1. Sorry, again you join the line passing through x2 comma f of x2 and x1 comma f of x1, and you pass it through the x-axis, and again it will intersect x-axis at a unique point, and that unique point is your next iteration in the sequence, and we are calling it x3, and you keep on doing it. So geometrically the picture is clear, and we saw this derivation of the method, and hence we discussed some convergence. So this is the full-fledged convergence of the secant method. So let us prove it. Proof. We first claim that for each n equal to 2 comma 3, with xn minus 1 not equal to xn, not equal to r, there is a real number there is a real numbers there are real numbers, sorry. Let's say zeta n and xi n such that xn plus 1 minus r times f dash xi n, this is equal to xn minus 1 minus r times xn minus r by 2 times f dash zeta n. Now let us say this is my claim 1. So claim 1. Now let us prove this. From the secant method, from the secant method formula, we can see that x is actually equal to xn plus 1 is a root of the equation, gx equal to 0. Okay, let us write it like this. Gx equal to 0, where our gx is x minus xn minus f of xn minus 1 by xn minus xn minus 1 plus f of xn, right? So let us check it quickly why this should be 0. You see g of xn plus 1, it will be xn plus 1 minus xn, okay, times f of xn minus f of xn minus 1 by xn minus 1. Now if you look closely, and here you have f of xn, this value from the secant method is precisely minus f of xn, right? So hence this is 0. Now this being verified, let us move ahead. For any given real number x not equal to xi, I varying from n minus 1 to n, We define a function we define the function xi t as f of t minus g of t minus f of x minus g of x minus xn minus 1 and x minus xn times t minus xn minus 1 times t minus xn, and t belongs to R obviously. So it is easy to see that you just see that number one, xi is a C2 function. Why? Because f is a C2 function, and the way we have defined g, it is a C2 function. It is just a polynomial, right? G is a linear polynomial, so anyway it is C2, and xi is made up by adding certain C2 functions. So xi is a C2 function. Number two, xi x is 0. Actually, xi xn minus 1, and xi xn, they all are 0. They all are 0. You just check. You pause the video and just check whether or not xi of x will be 0, xi of x n minus 1 will be 0, and xi of xn will be 0 or not. So from Rolle's theorem, from Rolle's theorem, we get two real numbers xi1 and xi2 such that such that xi dash xi1 is 0 and xi dash xi2 is 0. Now you see, because xi is a C2 function, xi is a C2 function, so we could go to xi dash, but again xi dash is continuous. So again, using Rolle's theorem, we obtain a real number lying between xi1 and xi2, which in turn are lying between x1, xn and xn minus 1 and xn. So this real number, let's say xi n, let me just write it here. Let's call this real number zeta. So real number zeta lying between xn and xn minus 1 such that, so this is the final number, this is the number zeta n such that xi double dash zeta n is 0. Now if you compute xi double dash xi n, what it will be? So if you compute, you will get, I'm writing it directly, fx minus gx equal to half of x minus xn minus 1 times x minus xn times f dash zeta n. So you just take your time and verify this. Okay, I am stopping for a few minutes. Yeah. So hope you have verified this. So in particular, you can take x to be r because see x was an arbitrary point. So this function gx, x was an arbitrary point. Okay, so you can take x to be r. Then the above equation, just a minute. Yeah. Okay. Just a minute. I think my video has just got hanged. Just a minute. So some network issue I have been facing right now. We'll join soon. Okay, so yeah, yes. I guess I've joined again. Just a minute. Is it being recorded? How do I check? Start again. Reduces to minus gr. Why? Because f of r is 0. You see, f of r is 0. Because r is the root of f. Is same as half r minus xn minus 1, r minus xn, and f double prime zeta n. Now, since g of xn plus 1 is 0, we have verified this above. So we can write the above equation as, we can also write, just a minute, I'm just scared like if the recording is going on or not. Okay. It shows here if the recording is being done. Okay, I'll trust this machine. So we can also write g xn plus 1 minus g of r to be same as half r minus xn minus 1 r minus xn f double dash zeta n. Now we will use mean value theorem. So using mean value theorem for g, we can find uh, xi between xn plus 1 and r such that, again some technical glitches happening. Just a minute, I'll open a file just to check whether this recording is being done, because otherwise I have to do it again or write a mail to the NPTEL authorities. Okay, let us try to play this. Okay, so let's move ahead. So yeah, so one can find an xi between xn plus 1 and r such that xn plus 1 minus r times g dash xi is actually half r minus xn minus 1 r minus xn f dash zeta n. But from the definition of g, we can see that g dash xi is same as f of xn minus f of xn minus 1 times xn minus 1. Now, since f is continuously differentiable, since f is continuously differentiable, we can again see this proof is using mean value and Rolle's theorem again and again. So you have to be uh, very explicit about the statement of mean value and Rolle's theorem. So we use again mean value theorem to get a xi n between xn minus 1 and xn such that g dash xi, which was this quantity f of xn minus 1 upon xn minus xn minus 1. So g dash xi will be f dash xi n, and if you substitute this, substituting this in the above expression, We get the in the above expression. Let's say this is 2. In So you substitute this in 2, and then we get the first claim. We obtain 1. Okay. So you just look at it now. I'm just going to check whether or not this is working. Put R, and you are moving in this direction, and eventually you will go to the original root R. And that is precisely the idea of the Newton-Raphson method. We'll see some derivation of it in the next class, but let us see what we have done today before finishing. Okay. So we so in the last class we have discussed the bisection method. So in the beginning of this session today, we started with the secant method, which is the root. So see, throughout the discussion from past few classes, the aim has to be how to find the root. So we have obtained the first claim. Now let us move ahead. Since R is a simple root, of fx equal to 0 and f prime is continuous, if prime is continuous, so we can always find a delta naught, right? We can find a delta naught greater than 0 such that f dash I is not equal to 0 for all xi in r minus delta naught, comma r plus delta naught. So the required delta lies between 0 to delta naught, which we need to choose. So it needs to be chosen yet. So for this purpose, let us introduce the following notations involving delta. Following notations using sorry involving delta. So for example, you choose m to be the minimum of just a minute r minus delta. You choose minimum over this of f dash xi, and it has to be strictly positive, right? and capital M to be why the minimum is strictly greater than 0, because so the minimum will be attained in this compact set r minus delta to r plus delta, and we know in r minus delta naught comma r plus delta naught f prime xi is never 0. Okay, so if this small m is 0, it means f prime xi is 0 for some xi between r minus delta comma r plus delta, which will be a contradiction. And the same logic works for the maximum. This will also be strictly greater than 0. Now let us start choosing our required delta. Let us choose our required delta such that whenever x0 and x1 they are in r minus delta comma r plus delta, with x0 not equal to x1, with x0 not equal to x1 not equal to r, we have epsilon to be maximum of m capital M by 2 small m times x naught minus r, comma m capital M again and by small 2m max upon 2 times minimum. Yeah. And so this epsilon we choose, and this is strictly less than 1 obviously. Why it is strictly less than 1? You see, because see x naught minus r is less than delta. So you can choose delta small enough such that this epsilon turns out to be less than 1. So then using 1, then using 1 with n equal to 1, we can see that actually modulus of x2 minus r is less than equal to m by 2m times x0 minus r times x1 minus r, which is less than epsilon delta less than delta. So therefore we can say that x2 belongs to r minus delta comma r plus delta, and further, since mod x2 minus r is less than equal to mod x1 minus r, we can use, let us write here, we can use induction technique to conclude that xn indeed belongs to r minus delta to r plus delta for all n equal to 2 comma 3 and so on and so forth. Just a minute. Yeah. Since f prime does not vanish in the interval, r minus delta to r plus delta, the way we have chosen our delta, so we see that f is a strictly monotone function in this interval. Why? Because you see, if you have a function like this, f is a continuous function, and let's say this is your r minus delta and this is your r plus delta. If it is not monotone, then it has to take a turn, right? Something, and the point where it takes turn, it will be the point where f dash xi is 0, right? So it will be a contradiction. So hence it is a monotone function in this interval. So this shows that it is 1 1, right? A monotone function, strictly monotone function is 1 1. Yeah, I should write strictly as it is strictly. So this shows that f is 1 1. What does it mean? That f of xn cannot be equal to f of xn plus 1 because xn's are not equal to xn plus 1. So for any n in the natural set, hence this xn is well defined. So hence, so first point was xn's are well defined. So this was the first assumption. This was the first conclusion that this sequence xn is well defined. You see, so we have proved this. This is a long proof. Yeah. Also, you see, you note that uh, this entity is smaller than, as we know, we have discussed it above. So mod x2 minus r is smaller than m by 2m times mod x1 minus r times mod x naught minus r, and the way we have chosen epsilon, it is nothing but epsilon square, strictly less than or equal to epsilon square, because our epsilon was this. Okay. Yeah. Now again you go and now you do the same computation with x3 minus r, and you see it is smaller than m by 2m times mod, You just see that. So it will be smaller than x2 minus r times mod x1 minus r. Okay. But x2 minus m by 2, this quantity is again smaller than by above m by 2 m square, or directly, now directly you conclude. So this is less than, just a minute. Yeah. I'm just thinking. Oh, we forgot one m by 2. Yes. Here we forgot one m by 2. Yeah. So now this quantity is smaller than epsilon square, and this is smaller than epsilon. So it is epsilon cube. Okay. And if you keep on doing this, you will get m by 2m xn plus 1 r minus r mm, is less than equal to, oh, the screen stopped. Yeah. So this is m by 2m times mod xn minus r times m by 2m again times mod xn minus 1 minus r. So you keep on doing this and you will get some epsilon and some power of epsilon. Okay. Where this qn is obtained like this. So it is a Fibonacci sequence with q naught is same as q1 is 1. Yeah. Yeah. So now, see, as n goes to infinity, this Fibonacci sequence Qn, this goes to infinity, right? And as Qn goes to infinity, this implies epsilon Qn plus 1 goes to 0, right? Because see, epsilon is strictly less than 1. So hence this shows that xn plus 1, or let's say xn, converges to r as n goes to infinity, because this side goes to 0, so this side will go to 0. Comparison test. Okay. From where does it follow? It follows from comparison test. So this was actually, if you note, this was the second statement that we needed to prove in the, yeah. So we have proved that there is a sequence xn in the interval r minus delta to r plus delta. Also, we have Also prove third point, that is xn converges to R. So it only remains to show that this limit is the fourth point precisely. Yeah. So all it remains is to obtain the order of convergence. So which means we need to find a constant c greater than 0, just a minute, such that, sorry, constant c greater than 0 and a real number. We need to find two things. Let's say alpha greater than 0. Alpha will be the order of convergence precisely, such that xn plus 1 minus r is less than equal to c times mod xn minus r times alpha for sufficiently large n. So in particular, or other way it can be stated as, in particular, if you are able to find c and alpha such that limit n goes to infinity xn plus 1 minus r by xn minus r, this limit is c. So we need to find such alpha and c. So again we should see, we again use 1. Huh? So using 1, we obtain that xn plus 1 minus r by xn minus 1 minus r times xn minus r to be same as f dash zeta n by f dash zeta n, oh sorry, 2 by xi n, and this we can rewrite as, so this can be written as xn plus 1 minus r times xn minus r by mod alpha, you just divide by yeah, so it is same as f prime zeta n by 2 times f dash xi n, its modulus, times xn minus 1 r times xn minus r 1 minus alpha. Okay. So where alpha is an appropriate number to be found later. So again we do some manipulations and to find alpha we further rewrite the above equation as so what we do, yeah, so left hand side is as it is and then xn minus r by xn minus 1 minus r times alpha whole power beta. So beta is actually 1 minus alpha, where beta satisfies the equation beta equal to 1 minus alpha and alpha beta is minus 1. So if you solve it, so we solve this for alpha. So how should we proceed to solve this for alpha? You see, 1 minus alpha is beta and beta is actually minus 1 upon alpha. So this implies alpha minus alpha square is minus 1 and hence alpha square minus alpha minus 1 is 0. So if you solve it, alpha is actually 1 plus you use the quadratic formula b square minus 4ac, b square minus 4ac, yeah, by 2. So therefore alpha has to be 1 plus root 5 by 2. We choose the positive square root and this is precisely what we need to prove. I mean, this is precisely the candidate for the order of convergence. So in this way we get this. Now, so by the sandwich theorem, we see that since zeta n converges to R and xi n converges to R, and therefore we have limit of this quantity to be equal to f dash R. Why? Because see, f is a C2 function. Again and again we are using the continuous twice differentiability of f. So combining all this, we get that limit n goes to infinity, xn plus 1 minus r by xn minus r alpha is same as f double prime r by 2 f dash r limit n goes to infinity xn minus r times xn, just a minute, yeah, xn minus 1 minus r mod alpha times this. So you just put everything, okay? You see, we have this limit, and if you put it here, we'll get the required thing, okay? Yeah. So finally, so alpha we have been able to find out. Now we seek the finally we seek C such that C is C minus 1 by alpha, okay? And clearly, because the property of alpha, this solution is C equal to this. One by alpha. And this fortunately completes the proof. So this was the longest proof in this discussion session that we have done. This completes the proof. So so now we have this convergence theorem, yeah, for the secant method, and yeah. So see, the point is this convergence theorem assumes certain things. For example, the function that you're working with, it should be C2, that is continuously twice differentiable function, and R should not have, F should not have any other root. Like, what I want to say is that any root of R is a simple root. If there is such function, then we can apply this secant method, and it will ensure the convergence around R. Okay. But again, the hypothesis, see, even in the conclusion, you should note that you have to choose your initial values to be sufficiently close to the simple root small r. Okay. So yeah, so we have completed the proof. So maybe I will discuss the next method briefly. And that method is called the Newton-Raphson method. I will maybe continue this in the next lecture also, but let's see how far I can go with this. A quick introduction is always possible. Yes. So it is again a root finding algorithm as we have seen in the secant method. This method is a root finding algorithm which gives successively better approximations to the roots of a real valued function. So again, this method, the aim of this method is nothing different than what we have already done and studied for the secant method. So the idea is to start with an initial guess. Okay, I'll just give the geometric interpretation. Then we'll continue this in the next lecture. The idea is to start with an initial guess, then to approximate the function by its tangent line. We'll see what do we mean by it. And finally, to compute the x-intercept of this line. What is the x-intercept? The point where the line intersects the x-axis. The x-intercept of this tangent line. This x-intercept will be a better approximation to the root and the next iteration in the Newton-Raphson method. Better approximation to the original function's root than the first guess. And you can continue this method for iteration to obtain the iterative sequence. The method gives a sequence of iterations. So geometrically see what is happening. You have xy axis here, and let's say your graph is this. Okay. So first what you do, you choose your initial guess. Let's say here, this is your x naught. Yeah. So this is your x naught. Oh, sorry. Then you draw a tangent at this point. What will be the tangent? Just a minute. No. I want to draw a tangent. So tangent will be something like this at this point. So the point where it intersects the x-axis precisely will be a second iteration. Sorry, the first iteration. So see, instead of working with 2 points, we are working with only 1 point, which is contrary to the secant method. But yeah, we will see. We need actually sufficiently smooth function for the Newton-Raphson method. Now again, you repeat this process. Okay. So now you draw the tangent again. Yeah. So your tangent will be like this. And where does it intersect? It intersects at x2. Let's say. So you see, this is the root. This is the root r, and you are moving in this direction, and eventually you will go to the original root r, and that is precisely the idea of the Newton-Raphson method. We'll see some derivation of it in the next class, but let us see what we have done today before finishing. Okay. So in the last class we have discussed the bisection method. So in the beginning of this session today, we started with the secant method, which is a root. So see, throughout the discussion from past few classes, the aim has to be how to find the root of a given function, and that function need not be linear. Now it can be any function, for example, sine x plus x square or something of this sort. So f can be any function. At any given point, the methods that we have been implementing, we need at least continuity of the function. So secant method is one of those methods which gives us concrete algorithm to find the approximations of a root of a given function, such that with every successive approximation it gets closer to the root. At least the idea should be like this. Okay. So what are the so the secant method works with the existence of two initial guesses. We have to guess two initial values x naught and x1, such that f of x naught is not equal to f of x1. Now, geometrically, we have already seen what do we mean, how do we do the method. You join the line you join the line passing through the points f of x naught, comma f of x naught, comma f of x naught, and x1, comma f of x1, and you continue this line to intersect at the point at the x-axis, and that will be a unique point, and that unique point we are taking to be our second approximation. Now you do the same thing for x1 and x2, you'll get x3, and you keep on doing this. So we formally derive the equation of this method. We saw some drawbacks, and the drawback is that if initial values are not close enough to the root, then there is no guarantee that the secant method converges. We saw one example, sin x plus x square minus 1. How does it work? Like just the implementation of the formulas. Now, the big shot of today's discussion is when we discuss the convergence of the secant method. So the hypothesis for this theorem is that we need a C2 function, and how to find the sequence via secant method which converges to a simple root of f. Okay, f need not be having a simple root at all, but we are adding this in the hypothesis. So for this particular class of function, we have a very good convergence in the secant method, and it is approximately equal to 1.62, which is more than 1 and less than 2. So the secant method is not quadratic. Order of convergence of secant method is not quadratic. Then we saw the proof. It was very long, but in the proof, one thing was very clear. You have to have an explicit. You have to make explicit use of Rolle's theorem and mean value theorem again and again up until the first derivative, and that is why we have taken f to be a C2 function. Then in the last, I tried to discuss this Newton-Raphson method, but due to shortage of time, I think it will be a better idea to discuss this in the next session. So unlike secant method, Newton-Raphson method just did one approximation to start with. Later on, we'll see that whereas in secant method, you don't require in the formula, you don't require f dash, that is f prime. But for Newton-Raphson method, we'll assume that f is at least differentiable, once differentiable. If a function is once differentiable, then you can apply Newton-Raphson method then the rather than the secant method. So you just need one initial guess, and Newton-Raphson method under certain hypothesis will ensure that the method converges. It gives you a sequence of iteration approximations which converges to the root of the function. Okay. So yeah, just a minute. The screen just stopped. Yeah. So in the next session, what we'll do, we'll discuss Newton-Raphson method. Mm, We'll be discussing Newton-Raphson method. Its geometric motivation we have already discussed, but with the help of this geometric motivation, we will be deriving the formula for the Newton-Raphson method as we did for the secant method. Once again, it is not that difficult. You just compute the tangent line equation, and your next iterant will be solving the tangent line where it intersects x-axis. So then we'll see some example. Then the convergence for Newton-Raphson method. Yeah, so maybe we will move into that direction. Then after that, we'll see interpolation problems. Yes. So yeah. So all these methods that we'll study are highly useful in the numerical computations, because most of the time the problem is you don't know the root, and it is not always possible to explicitly find a root. But given a certain error bound, you can always approximate this root via these methods, secant methods and Newton-Raphson method. And there is another method called regular falsy method, which is a pre-generalization of secant method, or of which secant method is a generalization. But all these three methods give more or less uh, the a good approximation to the root, one over another might be better, but that is up to the usage of the function. So you have to be very careful which method to use, because when you will be submitting these method to the computer, and it is always better to save time. Less computations means less propagation of error, as you studied in the beginning of this numerical analysis course. If there is an error at some stage, say 1 or 2, and if any computation involves that particular value, so the error will be propagated. So we don't want that. Okay, so always the less computations are better. So you have to choose a method. For example, for a given function, you can always apply secant method or Newton method, let's say, for a given function. Then you have to choose which method to apply. Which method will be better. Okay. Even if both the method converges to the same root, it might so happen that one is converging to the root. Given a certain error count, secant method is giving that value, let's say, after 10 iteration, and Newton method is giving, let's say, at 15 approximation, or the other way. So you have to choose which method. Obviously, the method which gives better approximation at less iteration is always better. Okay. So with this we finish.